2.7. Technically, it's velocity and other rates of change, but to be honest, we're going to be focusing on velocity. There's not a whole lot of other stuff in here besides that, but there's a little bit. So we're looking at application problems related to derivative function. If you've taken a physics class, this will all seem familiar. The big ideas of straight line motion will be revisited many times throughout our course with increasing difficulty. Now, part of what we're doing is interpreting the derivative in context to real world scenarios, like, you know, if it says the derivative of 5 equals 10, what does that mean in that scenario? So one thing, though, to point out, we are looking at, there's a couple different derivatives, notation derivative. One of them is Lagrange. Actually, Lagrange's notation. And that's honestly probably the one we prefer, and that's the prime mark. So when we say y prime or something, find the derivative, that's Lagrange's notation. And the most common modern notation. And then the original notation goes to Leibniz. And Leibniz notation is the dy dx. And the nice thing about that one is that it shows that it's the units of y with respect to the units of x. And so that's your Leibniz notation. Okay. So a little bit of information there. Okay, so suppose that S equals f of t gives the distance in feet of an object from a fixed point as a function of time t in seconds. So notice that the original function is defined as it's a distance, okay? What is the common term for ds dt? So the derivative of s with respect to t. What would be the derivative of distance? Or what would be if we change, I don't know, I want to say change distance to a rate, but when you go from distance to a rate,
like,
think physics here.
I guess I don't know what we're asking.
Yeah, and I don't know. That's why I'm realizing that I'm not asking it exactly right. Basically, we're looking at the fact that the derivative of distance is going to be velocity. So they're trying to get you to think about velocity being the derivative of distance or position, because when we do the derivative, it takes something. So think ds dt, so that's going to be so much distance per time. And that's like velocity is like meters per second or feet per second. Okay. Now, part of what we're doing is some interpreting here. And with that in mind, they ask us to describe the following notation in real world terms. So it's ds dt, and then that bar is like an evaluation bar. So we're saying evaluated when t equals 4. Well, what's ds dt mean?
Velocity.
Velocity. It's also the derivative. And when we talk about the derivative at a point in time, don't forget about IROC. Okay. So it's the instantaneous rate of change of an object. What's the t equal 4, tell me?
At t equals at 4 seconds.
At 4 seconds. Okay, so this is the instantaneous rate of change, or the IROC of an object. It's going to be in feet per seconds, because that is what is given in the prompt when t is 4 seconds. Okay, so can I just write IROC? Instantaneous rate of change. I'm just going to shorthand it, IROC. So IROC of an object in feet per second when time is 4 seconds. Okay. Okay. Now, go one step farther. What is the real world meaning of f prime of 4 equals 18?
At time 4 seconds, the IROC, or the velocity of an object, can be 18 feet per second.
Exactly. When t is 4 seconds, the velocity of the object is 18 feet per second. When t equals 4 seconds, the velocity of an object is 18 feet per second. Now, I have a little side note down here, and I don't even know if I can fit in, but I should probably put the information in there in that kind of my starred comment here. Positive velocity. I need you guys to understand that positive velocity tells me the object is moving away from a fixed point, okay, as opposed to negative, which is going to take it back to that fixed point. So I am going to put that, well, I was going to try and put it right here. I don't know if you guys have room or not, but
Well, technically, can it be negative then if it's heading away from it in the other direction? Because you're not changing directions then.
not with, so it's a hard question to answer when we're not in a scenario. Does that make sense? I don't have a definite answer until we get in a scenario, and then it'll be easier to answer that. How did I write that? Tells me the object is moving. Oh my gosh. Object is moving away from a fixed point. Okay, so positive velocity tells me the object is moving away from a fixed point. Okay, example 2. Did Neil Armstrong step off the lunar module and pick up a moon rock from the surface of the moon on July 20th, 1969? If he did, scientists say that the rock would have a velocity of 24 meters per second, or about 86 kilometers per hour. The height of the moon rock can be modeled by this function, s of t equals 24t minus 8/10 t squared meters in t seconds. A asks us to find the velocity and acceleration of the moon rock as a function of time. What did we learn yesterday? They gave us a position function. S of t is a position function. It's the height of the moon rock. What's the relationship to velocity from position?
Velocity is the derivative of position.
Right. So they're asking us in order to find velocity, we're going to find s prime of t, which is velocity. So velocity of that function is
24 minus, would it be 0.16t?
How about 1.6t? Although, thank you, because I did have a squared on there that I shouldn't have had on there. Okay, so yeah, 2 times 0.8 is going to be 1.6. There's only one decimal place in there to carry through. Okay, so that's going to be your velocity formula. And then what about acceleration?
Well, acceleration is especially distance over time squared, so it'd just be a second derivative, wouldn't it?
It is. It's a second derivative. So acceleration is the second derivative of position, or if you prefer, it's the derivative of velocity. That is your acceleration. What is the derivative of velocity going to be here?
Just 1.6.
Did you say minus?
No.
Be negative 1.6.
I mean, yeah.
Okay. Now, on that, notice in the comments it said the acceleration will be the acceleration of gravity on the moon. So that negative 1.6 is the acceleration of gravity on the moon, and that would have a label of meters per second squared. Okay, that's your typical label for acceleration. Velocity is meters per second, acceleration is meters per second squared.
On Earth, it's 9.81.
When we're working in meters. We also work in
I
feet.
know, I'm just saying.
Yeah.
9.81. Well, that's what you do in physics, is metric system.
I have confused people in the past because in physics, you guys only work in meters. In calculus, they throw both at you. So, okay, B. How long will it take for the rock to reach a maximum height?
So it's
So when will the rock, what do we have to think about here? When will the rock reach a maximum height?
when velocity is 0.
When velocity is 0, right? Because we're thinking about this moon rock, it goes up and comes back down, right? So maximum height is going to be up here. That's going to be, you can either think horizontal tangent line, right? So when the derivative is 0, or when velocity is 0.
It's a distance over time graph. That means the slope is 0 to the velocity.
Okay. So take your velocity and set it equal to 0. So my v of t is 24 minus 1.6 t, set equal to 0, and solve.
Whatever 24 divided by 1.6 is.
I agree. And according to my notes, it's 15. And the label is seconds. Okay. So how long will it take for the rock to reach a maximum height? And that is 15 seconds. Now, 2 more questions related. How high did the rock go? And when did it hit the ground? So first of all, how high did the rock go? What am I going to figure out there?
You can just take the initial equation and plug 15 in for t.
Okay. The max height happened at 15 seconds. We were given a position formula or a height formula, so plug 15 in. So you are indeed finding S of 15. So 24 times 15 minus 0.8 times 15 squared.
Not a good day, not have a calculator.
You want the answer? It's 180. And I don't even have any steps worked out on mine. I just have 180. So some of the stuff is going to be calculated. They didn't specifically say one way or the other on that one. So 180 what? Meters, because this is how high did the rock go? When did it hit the ground?
So you would just plug 180 in for S of t and solve from there for t. Or you could, no, that would work out because 10 t squared. Well, no. I was just going to say 30 seconds. But
Possibly. So mathematically, though, what do we do? When it hits the ground, what do we know?
That the velocity is 0.
Don't think velocity, because the velocity,
Acceleration is 0.
no. In algebra, I use this. When it hits the ground, the height is 0. You're trying to use calculus, and we really don't need a lot of calculus for this one. If they're giving us a position formula, we're looking for when does S of t equal 0. So when does 24t minus 8/10 t squared equals 0. Notice there's two terms, a t term and a t squared term. So we want to think factoring, and we want to think about a GCF.
Yeah. So it'd be like, it'd just be negative 0.8 t.
That's what I would do. Yeah, use that negative 0.8 that is the lead coefficient on t squared and factor out the t in common.
It would be 30.
Yep. So negative 0.8 t squared divided by negative 0.8 t is going to be t, and I'm flipping around as I go. 24t divided by negative 8/10 t is t minus 30. Officially set each factor equal to 0, right? And so you would have times of 0 and 30. So 0 is because it started from the ground. 30 is when it hits the ground. The question was, when does it hit the ground? So officially my answer is 30 seconds.
So you can't just double it.
It is, well, and that's the thing. Noticing my original formula, it's a parabola, yes? T squared, it's a parabola. We know parabolas are symmetric. Knowing that the max height is going to be 15, then yes, technically you can. But my question becomes, how do I find it if I never had to find the max? Okay. Okay. Page 2. In our last lesson, we defined S of t as a position function of a particle or object. However, y equals f of x can be used to represent many different quantities, such as amount of rainfall, temperature of yams, volume of a cone, people infected by a virus, and other situations. The derivative will help us discuss how these quantities change at any given moment in time. So on this page, we're going to do put the equation into words type thing. So in example 3, the scenario is, suppose W of x is a daily quantity of water in gallons required by a palm tree of height x feet. Explaining the meaning of each expression in a complete sentence, including units. So W of x is daily quantity of water in gallons required by a palm tree that is x feet tall. What does W of 25 equal 38 mean?
So it'd be, 38-foot palm tree needs 25 gallons of water.
Reverse it. Because palm tree of height x.
Why does it say WX is water?
Well, so that's W of x. It's the W of x here is the daily quantity of water in gallons. So when you put x in, this 25 here is the x you're putting in. And x is the palm tree height. So it's saying that a 25-foot tree, and then W of x equals, so it's going to equal 38 gallons of water. So a 25-foot tall palm tree requires 38 gallons per day. "25 feet tall palm tree requires 38 gallons of water per day." Okay. B. they like to throw W negative 1 in here of 38 equals 25. Keep in mind that W of negative 1 is indicating the inverse. Okay. I don't know what you guys remember about inverse, but the idea is an inverse switches your input and your output. So normally on W of X, your input is X, so your input is the height of the tree, and the output is the amount of water required. For the inverse, it's going to switch your input and output. Now, it still really kind of means the same thing, but it's the idea that here, the height causes the amount of water to be required. With the inverse, we're going to say in terms of when a palm tree requires 38 gallons of water per day, then the palm tree is 25 feet tall. So it's more a matter of how you say it, but we have to start with the 38 because that's my input. So when a palm tree requires 38 gallons of water per day, the palm tree is 25 feet tall. A palm tree requires 38 gallons of water per day. The palm tree is 25 feet tall. Okay, that's your inverse. So when you see that negative 1 exponent, that's your inverse, and you're just reversing input and output. And C. C is a, what are we looking for in C? It's a derivative. And what I need you starting to think is when it's a derivative is a rate. Okay? Like we think of derivative as slope of the tangent line. That's the rate of change of that tangent line. So here, because they're asking for a derivative, they want the rate. 25 is my input, 6 is the output. So the 25 still means X here, so still means 25 foot tall palm tree. Now it's a rate. It's not saying that it needs 6 gallons of water per day. It's saying the amount of water needed is increasing at a rate of 6 gallons per foot. When the palm tree is 25 feet tall, the amount of water needed daily is increasing at a rate of 6 gallons per foot. Okay, so that's the new one that we kind of have to work with here. When a palm tree is 25 feet tall, the amount of water needed daily so there is so there's going to be a hole there. Okay, so non-removable amino asymptote. So there's going to be a hole here because you can factor out an x there.
Okay.
So it can become like x times x plus 6. So if you factor out that x, then that x on top, you can't put that x on bottom. Okay. Does that make sense? Okay.
I will go tell her.
Okay.
Thank you.
You're welcome. The amount of water needed daily is, this next word is key, increasing at a rate of 6 gallons per foot. Now, a rate's either always going to be increasing or decreasing. This one is increasing, and it was increasing because it was positive. If we'd had a negative derivative, then it would be decreasing. Okay. So yeah, one of the things I know you'll have to do in homework when you get there is to go through and give explanations. Okay? Okay. It is acceptable practice to merely say rate of change for some moment in time or other event to represent the instantaneous rate of change, or IROC. Then there will be other instances where you must decipher the task from the scenario. Let's look at this case. So suppose C of T represents the cost in dollars per day to air condition your Florida beach house when the temperature outside is T degrees Fahrenheit. Explain the meaning of C prime of 90 equals 0.37, in a complete sentence.
When the temperature is 90 degrees, it costs 37 cents per day to air condition your house.
Almost. Except the way you said that, it would be, that's not the derivative. You're just saying if it's C of 90 equals 0.37. Because it's
when the temperature is 90 degrees, the amount of dollars per day is increasing by a rate of 37 cents.
There you go. Yep. So, when the temperature outside is 90 degrees Fahrenheit, the AC cost is increasing at a rate of 37 cents per day. Okay. The key things that, like when I'm grading something like this, I'm looking for increasing, I'm looking for the word of rate or something along those lines, depending on the scenario. Okay, and of course it's increasing because it was positive as opposed to negative. And a lot of this was based on the fact that they did tell you dollars per day up here and T degrees Fahrenheit. Okay. B, approximate the cost of air conditioning your beach house when the temperature is 94 degrees Fahrenheit, given that C of 90 equals 0.264 and C prime of 90 equals 0.37. Show your work that leads to your answer.
It'd be $4.12.
It would be. How'd you get that?
Multiplied 0.37 times 4 and then added it to 2.64.
Okay. Okay. Now, I'm going to set up a equation here.
And I did it in my head. So
I can tell. I can tell. I'm going to set up the equation so we have the idea behind it, but mathematically you did the right steps. So they tell us that on a 90-degree day, the cost is that 37 cents per day. Okay. With that in mind, that's our rate, yes? Think slope, think average rate of change. How do we find that rate? And it's normally like a y minus y over x minus x. So how I have mine set up, we're trying to find 94, right? So I did c of 94 minus c of 90 over 94 minus 90. And that's going to equal the 0.37. Okay. I know, but you need to be able to show the work. Okay. In certain scenarios.
Show the work that leads to your answer. I did show the work that leads to my answer.
But you need to be able to show it in this type of setup, not just the, I did these steps.
Why
So.
did you not tell me that?
Well, how much credit do you want on an AP exam?
They gotta be more specific. It's not my fault.
Okay. So, anyways, you can do some cleanup there. C of 94 is what we're trying to find. Minus C of 90, which was 2.64. All over 4 equals 0.37. As you mentioned, you took 0.37, you multiplied by 4. So if I multiply the 4 over, I now have C of 94 minus 2.64 is equal to 4 times 0.37, which is 1.48. And then if you add the 2.64 over, we find C of 94 to be 412. And what is that? That is...
At 94 degrees, it's going to cost $4.12 to rendition.
And that is $4.12 per day. Okay.
Pretty cheap, isn't it?
I don't know. I've never thought about that way. I really don't. I've never thought about taking our electric bill. Like it's on there when we get it from Duke, like the average cost per day, but I don't, know what it is. So, yeah. And the key to realize is we were looking for C of 94. So, okay. Moving along. Have we only gotten 2 pages done today?
Yeah.
Eesh. That's not a good thing. Well, there's not as much to do on this next page. Okay. So, we briefly defined particle motion and need to establish some vocabulary and terminology that connects position, velocity, and acceleration of an object to motion. These foundations will be used through our course. Now, the function s of t that gives position relative to the origin of an object as a function of time t is called a position function. We've already talked about that, excuse me. So s of t is generally speaking a position function. Consider an object that is moving along a straight line. These objects can either move horizontally or vertically. Can you give me some examples of any object, either natural or man-made? So what are objects that move horizontal?
Well, ball when you throw it.
I wouldn't put that in the horizontal category.
A car.
A car. I could put that in the horizontal category.
Technically, you could put a ball for any part of this.
Well,
The car.
what do we do? I have cars, people, boats. I have water and
Water.
rivers. I guess well, that one's kind of a tricky one because it kind of depends what do we mean in terms of water.
Depends what way the pipes are facing.
Fair enough. fair enough. But just in general on its own, you know. Okay, so horizontal, I mean, the big thing, the cars, the people, that type stuff. Now, vertical, think projectile here. Okay? Okay, and this is where balls come into play.
A bouncy ball.
Okay. When we think projectile, in terms of launching something.
A rocket.
Yep. And then I just have generally written anything subject to gravity. Anything, when you throw it up, it's going to come back, gravity is going to bring it back down.
Let's move it down.
Okay. So now, the function s of t, or notice they're also throwing in x of t, can be position. And notice it is position relative to the origin of an object as a function of time t. As the object moves, its position changes over time. Therefore, velocity is the change of the position function over time. This is the derivative. We've already talked about this. We can say that the velocity, v of t, is equal to s prime of t, or x prime of t. Let's clarify some ideas about motion and direction related to these ideas. So, instantaneous velocity, IROC, tells how fast something is going at that exact instant and in which direction. Okay? That is how the position is changing with respect to time, and that can be represented by any of these pieces, ds dt, s prime t, v of t, or notice, that's definition of derivative again. Okay, that hasn't disappeared yet. Okay, now, we're going to define motion of an object for v of t in the object below, or in the table below, excuse me. So, if we're talking horizontal line motion, if the velocity is greater than 0,
Going right.
it's going to move to the right. So if we continue, horizontal line motion, if velocity is less than 0,
On the left.
it's going to move left. If the velocity is equal to 0,
Stop.
stopped. Okay. Now, vertical line motion. If the velocity is greater than 0, it's going to moves up. If velocity is less than 0,
Down.
moves down. If velocity is equal to 0,
Rest.
okay, it stopped. I also have written in here, in parentheses as an option also, it could be at a max, because when the derivative is 0, it could be at a max as well. Okay? Now, that takes us to the end of page 3, so we got through a third of things. Real quick, speed. I may have to talk about this a little bit tomorrow, or it will come up, I'm sure.
Okay.
Got to remember a speed, okay? Speed does not indicate direction, and it is not the same as velocity. I still can't wrap my brain around that every day. You're going to do better than me because you've had physics recently. But, therefore, the speed of an object must either be positive or 0, which means the object is stalled or stopped. Speed tells how fast an object is going, no matter which direction, and speed measures the rate at which the position changes. Here's what you've got to remember. For our purposes, what we talk about, and I don't know, it won't even let me, speed is equal to the absolute value of velocity. I'm going with that as the same, as what you learned in physics.
Well,
But that's a big deal.
It is velocity is the vector version of speed. Because
Okay.
velocity has a measurement and a direction, where speed is just a measurement.
Okay, Eli, we got through 3 out of 9 pages, so we've got 6 more to go. Which, the next page we have to do is quick, but we've got some pages that are going to take us a while.
Those 1-2 pages are going to take forever.
Yeah.